Hi, my name is Anex and I'll be doing a talk on the primes of arithmetic progression. Just before we start, is there anyone else here who hasn't taken Calc 2 or doesn't know some complex analysis? Okay, that should be good. So we start with Legendre. He proposed that we have a sequence of arithmetic progression, so that means like we have Q plus L, Q plus 2L, and so on and so forth. He asked the question, when do we have infinitely many primes in the progression of the sequence? So when Q and L are not co-prime, that means that they have a common divisor. This is greater than 1. That means that in the sequence you have something like Q A times some odd number A times N2 and so on and so forth. So when N1 is not all the Ni is not equal to 1, you don't have a prime number in any order sequence. So the only time, well, we know that when it's co-prime, at least there's a chance that it could be a prime number. And Dirichlet proved that this is enough to show that there are infinitely many primes in the sequence, in this sequence. And he basically did, he had to show that this sequence, the sum over all primes, L naught Q 1 over P, this thing diverges. That means that there's infinitely many primes because it's not a finite sum, so there has to be infinitely many primes. So 2 weeks ago we did a similar proof by, we proved that, we didn't prove it, Professor Hartley proved that the sum over all primes from 1 over P is diverges by using Euler product, taking logarithm, and showing that the left-hand side diverges, so the sequence in here, the series here has to diverge as well. It's identical to that proof, but we'll be using more complex analysis, some Fourier analysis, and basic analytic number theory. It's mostly elementary analytic number theory, so you don't need to know many other theorems other than what I just said. So then we can skip the proof of this, right? Okay. So this is what we want to show. We introduce a notion called characters. So characters are functions from G to the complex number with modulus 1. And these are a set of 4 functions from G. It's usually abelian, so we don't have to care about other stuff. So this is usually performed in C2. It's a multiplicative group of modulus Q. So we start with an example we'll show that for primes of the form 1 mod or 1 over P, this thing diverges. Before I get into the abstract stuff. So we have 2 functions in the multiplicative group of Z mod 4C. There's only two elements in this group, which is 1 and 3, and we sent chi1, the trivial one. It sends to the identity, it's just the complex number 1. And the other one we have is chi1, another character. This always sends to the identity. Oh, I should mention, this is the homomorphism. And chi1, 3, another one. These are the only characters. And moreover, the characters are multiplicative. So chi is n, n is 5n, I n, And we can extend it to not just the multiplicative group, but over z mod 4z by setting chi of n to be 0 when n and q are not coprime. And so we're going to write out the sequence for chi of n, or n+, this is usually a representation of the Dirichlet L functions. It's of the form, it's almost like the zeta function, but you have chi of n is just a 1. So here we just get, for the trivial one, we just get that chi of 1 over 2 ds, 1 over 5 ds, and so on. For the non-trivial character, you get let the L function as 1. This is similarly the L function R0. And as approaches 1 from the positive side, you have that L chi 1. This approaches. Does anyone know what that sequence is? Series? It's the Leibniz phi. It's bounded. The point is that it's bounded. And so we know that L chi of 1 is bounded as s approaches 1 from above. And so we can take the identical to the proof for the infinitude of primes. You can take the logarithm of the L function. You get because chi is multiplicative, you also have this Euler product representation. For the zeta function, you have it because you have a unique factorization and primes factorize all the real integers. So you take the logarithm, it becomes a sum. You have this is the when you have a function for x small enough, you have the representation 1 minus x. You have x plus x squared over 2 plus x cubed over 3 and so on and so forth. You can write it as sort of like x squared. You can bound it by the this big O notation basically means that when you have two functions f plus g of x, it means that f minus g is less than or equal to m times x when x is large enough. That's basically what it means. We're bounding the growth of the logarithm by x has to be less than that. So we basically have sum over primes of pi of p over p ds plus it's basically that. I substituted in. Here we know this is a finite number because not just over the prime code, but if you let it run over all the integers, you know that that approaches pi squared over 6, so this thing is bounded. So you can bound it by a constant. So this is just it's less than a constant. And because this thing is bounded and the logarithm is non-zero, you have this thing over pi of p over pds is finite. For the non-trivial one, for the trivial one, you still have unboundedness. So that's the first part. You can separate it into the primes of the form p equals 1 mod 4 and 3 mod 4. This is from the summation, and we also know that this thing, the trivial one, this is just the sum over all primes. So we basically just add them together and we get that. Here we have 1 over p conjugate to 1 mod 4. And this thing is divergent because the trivial one is divergent, but the non-trivial one is bounded, so you can add them together, add the two series together, and you get that the primes of the arithmetic progressions of the form 4n plus 1 has infinite many primes. This is basically the gist of what we're going to do for arbitrary primes and arbitrary modulus, not just one. I think the easiest one, there's an easier way to do it in general for 1 mod p. We're not going to do that. We're just going to go straight into the arbitrary modulus, not just for. So, like I said before, Z to be, G to be the abelian group to be the multiplicative group on arbitrary modulus Q. And you define a function, delta L. It's the indicator function on the L on modulus Q. So you have 1 if n is congruent to L mod Q, and 0 over 1. So for any functions in the group from G to the complex numbers of the modulus 1, you have this Fourier representation, which is it's identical to the. You have to define an inner product, and you basically have to define an inner product on the group and take the summation. It's identical to the Fourier series for arbitrary, for the functions from the real to the real. You have something like the Fourier series of Anex 0 to 1 of x e to the negative 2 pi I Anex, and you have this representation. The Fourier inverse formula is basically n equals n in the integers. Either 2 pi I Anex. It's identical to that, but instead of working from functions from real to the real, we're working with groups. You have this this representation. This is the set of all characters. We define the homomorphism from g to the complex. We have this identical to the previous case, and we have the Fourier series defined by 1 over g. This follows because sorry, this is the I wrote it back, but this is the the Fourier representation. So you have the order of the group over the sum over the function times e of n, the character. In the other case we have e to the 2 pi I. Anex it's basically identical. And when we plug in this thing is 1 over g times u L, because it's the I should mention. And this is the key formula that we're going to use it to decompose it into just the sum of characters that we already know for any characteristic function. So you have delta L P, this is it's just the indicator for so that's just P mod Q, L mod Q, 1 over P is equal to, by the Fourier inverse formula you get this. This is this is the Euler P function, that's the order of g because it's a multiplicative group. We have sum of all primes times sum of all characters. I should mention, when I went from there to here, I used the extension function, not just on the multiplicative group, but also on all the the non-coprime numbers as well. This. So, like before, we isolate the trivial character because it's always a multiple of the zeta function. That's the only part where you have infinity showing up. The other characters are bounded. So like I said, to show that this thing is divergent, it's enough to show that this thing is bounded, the non-trivial, the sum over non-trivial characters is bounded, but this thing is unbounded, and you have the right-hand side is divergent, so you have this thing is divergent, and there's infinitely primes. So the other step, we took the logarithm of the L function. I was able to do it because chi of p is, the modulus is, the absolute value is less than 1 for in that case, less than or equal to 1. In general, when you have a complex character, this thing could be, the character could be complex and takes the logarithms, and you don't really have a single valued logarithm in the complex numbers, right? So you have to define it through the series expansion, take the exponential and show that you get the exponential and the logarithm are basically inverse for small f cubed. But I'm not going to show all this, I'm just going to cite that. I'm just going to cite this here that if s is greater than 1, you have this, you have the order product. And you can take the logarithm of the L function. You basically have something of the form sum over primes of logarithm sum over primes of 1 over p plus the sum bounded by 1 over p, yes. Should mention that. I left s first. This thing is a constant, same reasoning as before, and you have this, you can write it as a sum over primes of the characters, and everything is there. Now we get the key part. When I took the logarithm, I have to make sure that the chi function is the L function is not 0. It's not vanishing. You have to show that for any arbitrary non-trivial character, it's always the case that it's non-vanishing. If you do that, that's it. That's pretty much the whole proof. And for the you have two cases. You have either chi of p is plus or minus 1 or 0 for chi of n. For all n, or there's some complex, chi of n could be complex, and the complex case is rather not too hard, but the real case is what took Dirichlet the actual hard work, because if you actually look through the original proof, he introduced something called a class number formula and quadratic, discriminant of the quadratic forms. We don't want to go with that, it's too complicated, so we're just going to stick with the simpler case using elementary number theory. So we need to show that for chi not equal to the trivial one, L1 and equals to 0, and we can take the logarithm. The product over all characters of L chi equal to 1. Oh, I should mention all the non-trivial characters are not only defined for s greater than 1, but they're also continuously differentiable. So for s greater than 0, so you have much more flexibility than the normal compared to the trivial character and the zeta function, because you have continuous differentiability over s greater than 0. So all this is fine. So you know that as approaching 1 from the plus side, from the positive side, we have this thing is not going to suddenly go to 0, and it's not going to be 0. That's basically it. So you just take the exponential of that sum of that product, and you get a sum of all kind of the product formula you get. Now, this is a finite sum. These two may not be finite, but you can bring the kind to the inside, and I don't have to show all the uniform modes. Now, this thing, if you remember, it's the Fourier representation of a characteristic function. So this, you basically have something like delta L of n is equal to 1 over g from the order of g over all the characters I L, the conjugate I of n over. You have that. So basically, we have the identical thing, so we can substitute here. This is equal to the exponential of the sum over both times of k equals 1 to infinity, 1 over k over delta L, delta 1. When it's a trivial one, you just have it 1 everywhere, and you get that delta 1 piece of k. Now, when you take the exponential of this, all this is positive, and when you take the exponential of this, you get that this thing is should be greater than 1, less than or equal, greater than or equal to 1, and that basically shows that when you take the logarithm, you get this thing is greater than or equal to 1. For the complex ones, you have a bunch of propositions. If L and R equals 0, when you take the complex character, you get 0 as well. This should be obvious. When you have I of n or n to the s, conjugate is just 5 n to the s, and this first part, second part is by the way, the argument I'm trying to replicate here is that, except for the non-trivial one, you have you could have zeros at 1, and because you have a simple pole for the non-trivial character, the two zeros cancel out, and if 2 zeros cancel out with one of the poles, and you get a 0 there, and you have the contradiction that the product is not equal to 1, not greater than 1. This is basically, the second part is basically mean value theorem. Because of the continuous differentiability, you could just, this thing is L as minus L as 1 pi value theorem, and because this thing is continuously differentiable and we're on top of interval, you can set it back on this and basically say that this is less than or equal to c times s minus the actual value of s minus 1. That's the second part, and the third part is for chi naught, let's say chi naught, for chi naught. This is the simple pole I mentioned. This is the particle or primes p not dividing cube of 1 minus 1 over 1 minus times p or chi naught p over p. Yes. This follows because when p divides q, you have that chi naught is 0 by the extension that we defined, and you can rewrite this as just a data function times some. I should use one times the product over p dividing q of 1 minus 1 over p. And this thing is a constant, so we can show that. The only thing you have to take care of that the zeta function has it behaves mostly like this. This is just it's a standard trick. Basically, you have a zeta function from infinity n to infinity at n to the s. This is less than or equal to the 1 plus the integral from 1 to infinity of 1 over x to the s. Just follows from the graph after we graph it. This thing is the integral is always lower than the harmonic numbers, the Riemanns on the length 1. It basically follows from that. You could do it more carefully by defining the sum over n from 1 to infinity of n to n plus 1 over x to the s. And this thing, 1 over n to the s, because we're taking the right endpoint, you have this thing is less than that, and you sum over the integrals and you get this. Now this thing is just, this is just the usual integral. There's nothing too spicy about that. This is 1 over 1 plus 1 over x minus 1. And that's just s over x minus 1. That's an equality. And by that, you know that the non-trivial character also has something like this. S is, by the way, S is bounded. S is between 1 and 2, so you can just take you take this constant along with the largest s, and you get that this is less than or equal to 8 times s minus 1, and that's basically what we want to prove. So you have the product for all characters of L, S, I. This is 1 And if you extract the, you assume for contradiction that for some complex character L S of chi 0 as approaching n, you assume that, and you get this. You get that. You can extract the character, the complex character, and the non-trivial character, and cancel out the whole that comes from the trivial one. So this is the trivial character. Times on the finite. So this thing is bounded by s minus 1. And this thing is bounded by c times. I'm going to collect all the constants to a and just call it that. You have this thing, and this cancels out here. And as approaches 1 from the positive side, you have that this thing is approaching 0, and that means that that product is 0. That contradicts that there's the complex character vanishes. That's the first part. Now comes the hard part. I have to show that for real characters, you also don't have non-vanishing. We start with a bunch of dilemmas that's mostly should be mostly done in Calc 2, I think. We have some and this is log of n plus the Euler-Macroney constant plus the remainder term is just bounded by 1 over n. Visually, this just follows because we have this. When you take the difference between the harmonic numbers, the harmonic series, and the integral, you get these pieces. That's growth. That eventually goes to 0, and you have this. It converges to this constant for the Euler. It's the gamma constant by Euler. And similarly, you also have when you take the square root, you have 2 the square root plus some constant. This follows similarly because these functions are roughly the same. Well, if you take the logarithm, they're just constant away, so the growth is almost identical. So we introduce a function on 2 variables, and then both integers by I of n over the square root of n. The trick of composing products of Dirichlet, the multiplicative functions. It's pretty common in analytic number theory. You try to write to compose some as. So if you have k and equals k, can interchange it in a couple different ways, and they're all identical. Just I'm going to show a visual reason why. This is equal to this, which is also equal to this follows because basically what we're doing is we have a product, so like n equals k, and that's at most n, so you have this graph n equals n, here we have n. The axis is this axis is n, and you're basically trying to sum over all the integers underneath the graph. So you have this, you could either sum over the product, so like you can sum over the lines, the points in this way. That's the first sum. The second one is you're basically summing over vertically, and the second sum is you're summing over horizontally. They're all identical, and this is the trick you usually see in analytic number theory. So you have something called hyperbolic summation. We try to use symmetry to break this into like 3 different sums. Excuse my perfect one, but this could be a square, and these are like something like this. These two sums are identical. We call the S3 and S1. You could use symmetry here to get rid of dependence on n and m. So you have, I'm just going to say the S1, this is S1. That's just, when we write it this way, we can use a lot of symmetry to prove various things about arbitrary multiplicative functions. So for the real characters, we have a dilemma. Defining some Sn is defined to be 1 less n equals n less n, and m. So first proposition is that Sn is less than or equal to c times log n for some positive constant c. And the second proposition is to show that Sn is equal to 2 square root n L1. So, by the way, this chi is real, non-trivial. So if we have that, if you prove this proposition and we have that, this thing goes to 0, then we just have this. The sum is just it's just constant, and this contradicts the growth rate that we proved in the first part. That's basically the way we're going to prove that this thing is non-vanishing. First part we have you can take out the NM, the product, and take it out. Right, this is n dividing k for all integers n, for positive integers n, and you have, so we need n divided k times n. This we need a lower bound on this for it's strictly positive for all k, and it's greater than 1 for k of the form L squared for some integer. If you can show that, then that means that the Sn is greater than or equal to the sum over L squared less than or equal to n, because 1 over L squared. That thing is bounded by 1 for the squares. If you have this, then you have this is roughly L less than or equal to square root of n 1 over L. This is the harmonic and logarithmic difference, that it's positive, so this is greater than or equal to the integral here, it's basically c times, it's just a logarithm, so logarithm of root n, but you can pull the square root outside and just have n. So that's the first proposition. And the second one, I should mention, the way you prove this thing is by you do it for prime powers. So when you have k equals n divided p to the a, chi of n, this is just it's not too complicated. It's just I equals 0 to a, chi of p to the I. It's just all the divisors of the form p to the a are just powers of prime. So like 1 to p squared up to p to the a. And with that, you just do case proof. So chi of p is plus or minus 1 or 0, and depending on the case, you get that. Yeah, and you do it for primes. You show that this is equal to greater than 1. Then by the multiplicative property of the L functions, the characters, you have this is just a product over OPA dividing the largest prime power dividing k of this sum, that's just you get the same upper bound here. And with that, that proves the first proposition. For the second one, you need a couple dilemmas on top of limits. So you have b n equals a 5n over n. This is it's bounded by it's bounded below by n equals a, and similarly you have b n equals a 5 and other n. And to prove this, it's use a tool, another tool in analytic number theory called audible summation. If you're actually trying to prove like some of the theorems, some of the elementary Calc 1 theorems about convergence of series using Dirichlet test and a couple other tests, you will often use this. It's basically when you have a sum of the form n equals n a n b n. You can write this. You have something called symmetry functions. The effect is defined to be just the sum over all n less than or equal to x of b the n. This thing you can rewrite this in m n equals n b of n minus b. Let's assume that b of n minus 1 is 0. This one. And you just rewrite this as b of n for n from n to n minus 1, a n minus a plus 1 plus b of n a of n. That's the audible summation formula. It's also called the there's an integral thing. Anyway, we're basically going to use that for chi of n and square root of n to get a bound on the summation. We might not show the whole thing. But it's basically using mean value theorem with this lemma. Sum over all the elements from the multiplicative group is just 0. It just falls because you can extract when chi is non-trivial, you can extract like chi of n times a for assume that chi of a not equal to 0 for some a because chi is not 0 everywhere. And you use multiplicative property to write it as two sums, and you have this thing is equal to just I of n q n in 0 qz. You can extract the a outside and you get it. Because this is equal to 0 and this is not equal to 0, you have the sum over all the characters has to be 0. And with that, you have a bound on n less than or equal to any k with common fan. This is just, you can divide k by q, and k equals, suppose k equals k times q times a plus u, where u is less than or equal to q minus 1. And with that, you just do the triangle inequality, and you get n. This is less than or equal to, well, all the modulus is at most 1, so it's less than or equal to q minus 1. And you get that this thing is bounded. So with that, you can use, along with substituting for Bn, you substitute this thing, and you get the first proposition. Similarly, you can also do the same thing for the second proposition. And the final part is just breaking up the sum into the 3 parts that I showed before. It's just for the first part, you get s of I n less than or equal to the square root of n. This is just use the previous lemma that I mentioned, and you just get 1 over square root of n, and this is that's just the thing we saw before for the logarithm, for the sums of the form 1 over square root of n. It's just bounded by the square root of 2 square root of n plus some constant, and you have this 1 over square root of n plus a constant, and that's the first sum. For the second part, you combine the second and the third, you get some symmetry there. Basically, you get you rewrite the same thing, similarly as before. You get 2 square root of n plus some constant plus 1 over square root of n. And this thing is, you break it into 3 different sums, and you get this is 2 square root of n. You add back all the infinite, like, so to get the L function, you just add back all the sums of the form n, which means square root of n to infinity times n over n, and you just get the L in plus the constant. You can combine all these are just constants. You can combine all them together and you just get I think that's the second proposition. Yeah, that's it. Any questions?
Yes, when taking the sums, could you, when you were talking about them representing symmetries,
Yeah.
I was just curious, could you explain where that kind of comes from? Or like maybe if there's a simpler example you could use.
Okay. When we're working with multiplicative functions, in the group, it forms a group. The set of all multiplicative functions forms a group, and you have this operation called convolution. And when you have that, so if you have two multiplicative functions f and g, you have this convolution, and that's defined by k divided n of f of k g of n minus k. So the three different sum, it's usually it's usually in the form n less than or k, n less than or equal to n of f g n, and usually you have to bound the you have to do something called the average order or bound the sum. You need to show that, well, you take like, you know the divisor functions, right? The d of n is the number of divisors of n. If you try to bound that thing, you will use basically the same thing that I showed before. You would write it as three different sums, and you're trying to bound this thing, and I guess in that case you're taking the average order. Yeah, so you can ignore that. I don't think there's a simpler example. I think d of n is the simplest one there. Basically used to find the average orders.